Let's go ahead and give sort of an informal definition of what concave up and concave down means. So concave up, if you think of this thing like a dish, it would hold water. Concave down would spill water. So what's happening with a function that's concave up? So when you read from left to right, what's happening to the slopes at every point, right? So here the slope is negative. Now it's 0, now it's positive, now it's more positive. So the slopes, when you read from left to right, the slopes are increasing. Not necessarily the function, because, for example, here's a function that's decreasing in concave up. So, and again, the slopes are increasing. So for concave up, that means the first derivative is increasing. And so a way to test for when the first derivative is increasing is to see where the second derivative is positive, right? So that just follows from the stuff in the last video, right? Remember, a function f is increasing whenever the first derivative is positive. So that means the first derivative is increasing whenever the second derivative is positive. And so the same thing here for concave down. So here the slope is positive, less positive, 0, now it's negative, right? So here the slopes are decreasing. In other words, f prime is decreasing, and so we know that f prime is decreasing whenever the second derivative is negative. So this is the test, right? The second derivative test tells us when a function is concave up or concave down, right? So let's use that now to sort of get a better sketch of a function. So where is the thing increasing and decreasing? Where is it concave up and concave down? And a critical point of the second derivative, we will call that a point of inflection. Okay, let's get a sketch of this graph. F of x equals x squared minus 4 over x squared plus 4. And so before we look at the first and second derivative tests, let me throw another feature of the graph into the mix. So whenever possible, see if you can find the x and y intercepts, right? So the more points that you have on the graph, the better. And these are some good points to have on the graph. So remember, the x-intercepts, that's when the function is equal to 0. So you set this thing equal to 0 and solve for x. Right, so the graph, the fraction is equal to 0 whenever the numerator is equal to 0. And so you can factor this thing as x plus 2 times x minus 2. And so if this is equal to 0, that tells us that x is equal to plus or minus 2. So real easy. We've got 2 points on the graph, 2 comma 0 and negative 2 comma 0, the two x-intercepts. What about the y-intercept? Well, the y-intercept happens when x is equal to 0. So here I'm just going to plug a 0 everywhere I see an x. And so here I'm going to get just negative 4 over 4. That reduces to negative 1. So I can see that my y-intercept is 0 comma negative 1. So here are the three intercepts, negative 2 comma 0, 2 comma 0, the two x-intercepts, and the y-intercept 0 comma negative 1. And then if you can, check symmetry, because if the function has symmetry, then that can save you some work. In fact, it might be a good idea to check the symmetry like very first thing, because then we would know, right? We would know that if 2, 0 is on the graph, then negative 2, 0 is also on the graph. Anyway, to check for symmetry, always just plug negative x everywhere you see an x. If you get the function back, if you get the same thing back, so when I plug negative x in for x and squared, I'm just going to get x squared. In other words, I'm going to get the function back, then it's got y-axis symmetry. If you get negative the function back, then it's got origin symmetry. Hopefully we'll see an example of that a little later on. Well, in this case, we've got y-axis symmetry. So whatever we draw on the left-hand side of the graph, we'll have to draw that same shape on the right-hand side of the graph. Okay, So let's store this. I'll recall it a little later when we get ready to sketch this thing. So now we want to move to the first derivative test, see where the thing is increasing and or decreasing, and sort of jot down the critical points where there might be a local maximum and a local minimum. Where is this thing increasing and where is it decreasing? So first derivative test, this thing is a quotient, so I need to use the quotient rule. It's the derivative of the top, which is 2x, times the bottom, which is x squared plus 4, minus the top, x squared minus 4, times the derivative of the bottom, so 2x, and then divide all that by the bottom squared. So x squared plus 4 quantity squared. So now in order to find the critical values, we will need to simplify this thing, unfortunately. So here you can multiply all this out, and just do a little algebra. This will all simplify to 16x. So make sure you're good on how I got from here to here, right? That's just algebra. And I don't have room on the board to write that all down. So now, what are the critical values for this first derivative, right? So for this function f, right, where is the derivative equal to 0 and where is it undefined? Well, the bottom is never 0, right? X squared plus 4 is never equal to 0. And so x squared plus 4 squared is never equal to 0. So this thing is always going to be defined everywhere. So the only place where there's a critical value is where the first derivative is equal to 0. So we know that a fraction is equal to 0 whenever the numerator is equal to 0. And so when is 16x going to be equal to 0? Well, that's just at x equals 0. So we've got the one critical value at x equals 0. So I'll plot that down, write my factors off to the side, right? X squared plus 4 quantity squared is always positive no matter what. And then I want to check 16x. Well, when I plug a negative 1 in for x, I get a negative. And when I plug a positive 1 in for x, I get a positive. So here I get a negative and a positive. Now you want to multiply these signs together. So a minus times a plus is a minus. Plus times a plus is a plus. And so we can see this thing is decreasing from negative infinity to 0. Right, it's decreasing from negative infinity to 0 and then increasing from 0 to infinity. And so we'll want to remember this for later on when we sketch the graph of the function. And remember, f of 0, right, is negative 1. So we've already got this. We already know the y value of this critical point, right? We found that when we found the y-intercept. So now we want to check concavity. And then once we do that, we'll be ready to sketch the graph of this thing. All right, the last thing we need to check is the second derivative so we can determine where the thing is concave up and concave down. So I've got the original function. Here's the first derivative. And so again, we need to apply the quotient rule to find the second derivative. So it's the derivative of the top, so 16 times the bottom, x squared plus 4 quantity squared, minus the top 16x times the derivative of the bottom. So here we need the chain rule. So I'll bring the 2 down in front, recopy what's in the parentheses, and then tack on the derivative of what's in the parentheses. And so I get 2 times x squared plus 4 times 2x. So now we have to go about the unpleasant business of simplifying this thing. So I already did that sort of off to the side. Probably need to FOIL some stuff out, or if you want, you can factor out an x squared plus 4. That might make things a little bit easier. So anyway, when you simplify all this, you get 64 minus 48x squared. Again, this thing is never undefined, right? So x squared plus 4 is always positive. So the only critical value that f prime will have will be where f double prime is equal to 0. So I just set the numerator equal to 0. And so when you do that, you get 2 over the square root of 3, plus or minus 2 over the square root of 3, right? So if you like, this is really the square root of 64 over 48, right? And then after some simplification, you just get 2 over the square root of 3. Okay, so now that we've got our critical values for f prime, let's go ahead and plot those and see where the second derivative is positive or negative. Okay, so here are the factors of the second derivative off to the side here. I could have factored this thing, but I'm just going to use a little geometry to determine the signs. And then here I've got x squared plus 4. That thing is cubed. And so we know x squared plus 4, that's always positive, and the cube of that is always positive. So here we get pluses all the way across. Now, what about 64 minus 48x squared? We know these are the roots of this parabola, and we know that this parabola is upside down. So here's a picture of this parabola, right? So here's negative 2 over square root 3 and 2 over square root 3. So what do the signs look like here for this part of the function? Well, it goes from negative, and then after negative 2 square root 3, now the thing is positive, and then so to the right of 2 over square root 3, then the thing is negative. So these are going to be the signs for this piece. And so now all we have to do is just multiply this stuff together. So a negative and a plus is a negative. So I know it's concave down here. A positive and a positive is a positive. So I know it's concave up here. And then a negative and a positive is negative. So there it's going to be concave down. So now let's sort of assemble all of the information that we have to sketch the graph of this thing. Let's assemble all the stuff that we figured out here along the way. So our intercepts, negative 2, 0, and 2, comma 0. So here those are. I plotted them. And then the y-intercept, 0, comma, negative 1. And then we know we've got y-axis symmetry, so I know that the thing has to be symmetric about the y-axis. So if I fold the left-hand side over, it should match the right-hand side. And now I know I've got a critical value at x equals 0, and that y value is at 0, comma, negative 1 again. So that's negative 1. And I know I'm decreasing from negative infinity to 0 and then increasing from 0 to infinity. I know I'm concave down from negative infinity until I get to negative 2 over square root 3, and then that switches to concave up from negative 2 square root 3, 2 over square root 3 to positive 2 over square root 3. So from between these two things, it's going to be concave up, and then it switches back to concave down when I get to the right of 2 over square root 3. And so because concavity switches, we've got points of inflection at negative 2 over square root 3. And so what's the y value? So just take this thing and plug it back into the original function. You'll get negative 1/2. So here's the point of inflection where these x's are. And again, when I plug in positive 2 over square root 3, well, I know it's got y-axis symmetry, so I still better get negative 1/2. So we go from decreasing and concave down, right? And then at this point, it switches to concave up, and it stays concave up until I get to this point. But it's still decreasing, and now it switches to increasing, and now it switches to concave down, right? And then it stays concave down and increasing. So this would be a good final answer. We'll see what happens out here for the large values of x. If you want, you can just take a limit as x goes to infinity and see that you get y equals 1, right? So there's going to be horizontal asymptotes, but we'll come back and revisit that part later. So here's just a good rough sketch for this thing for right now. So make sure you're good on all 4 of those steps, and make sure you see why this graph looks the way it does based on all of this information that we gleaned in the previous 4 parts.